Collision theory states that in order for reactants to do their good little reactant thing and turn into a product, they first have to collide. Not only do they need to collide, but they need to collide in the correct orientation and with enough energy. We'll start with that whole collision thing. Let's take a reaction of, let's see, what should we have? Let's have lead to nitrate. Nitrate's lead to nitrate, there we go. And we'll react this with potassium iodide. Okay, we are going to form certain products. Now, this is a metathesis reaction. It's a double displacement. Essentially, the cations, the lead to and the potassium, are going to switch places, right? So that is going to leave us with potassium nitrate. Now we've got two nitrates, so we're going to have two of these. So we're going to have to start with two of those. There we go. We're balancing as we go along, and we're also going to get some lead to iodide. Lead to I2. There we go. So that's our reaction equation there. Now, this stuff, the lead to iodide, is a nice yellow color. In fact, let's highlight the whole thing. There we go. That is yellow in color. So we'll know when we've got the reaction. We should see some yellow. Okay, let's do the reaction. First up here we have a test tube of lead nitrate and a test tube of potassium iodide. And we're simply going to tip one of the solid on top of the other. And this is the result. You can see from this that we do in fact have some of that pretty yellow lead to iodide. That's great, but we don't have it all throughout the mixture. Where do we have it? Just in the middle, where the potassium iodide is actually touching the lead to nitrate. So this really demonstrates the collision theory, because that's the only place where the reactant molecules can collide. Now, if we stopper this test tube and give it a bit of a shake, this is what happens. So now you can see we have much more yellow, because in shaking the test tube, we're allowing more of the reactant particles to collide with each other. Okay, remember the collision theory says reactant molecules have to firstly collide with each other. Okay, so by shaking, we're allowing more of those collisions to take place, to occur. There's one more thing we can do, and that is to dissolve a bit of each of these solids in water. So we make an aqueous solution of each of them. As we have here, we have aqueous solutions of lead to nitrate and potassium iodide. And we're simply going to mix these now. And this is what we have. Now this is even a much brighter yellow, right? We've really got that lead to iodide forming now. Not only do we have it really forming very well, so the reaction's taken place really, really well, it's actually a very fast reaction. Let's take a look at actually mixing these two solutions so we can see just how fast it goes. This is how we can mix in a test tube. Hold it firmly at the top and knock it down with the test tube on an angle. So the salt hasn't all dissolved, but that's okay. We will have some in solution. And now when we mix them, we see this happen. Straight away we get a lovely yellow precipitate forming. So there you go, very, very fast reaction. Now, the first thing was collision theory, right? We've shown that. We've shown that the reactant molecules need to actually collide. So when they weren't colliding much, only where the two layers were touching, we just got that yellow line, right? The yellow line of the lead to iodide. When we shook the test tube up, when we mixed them more, we had more chance for the reactants to collide with each other, and so we got more of a reaction. Now, when we have them in solution, let's go back to our equation. Here it is. Let's just get rid of that yellow so we can see a bit better. There we go. What we did now is we actually made a solution of the potassium iodide and a solution of the lead to nitrate. Now, all nitrates are soluble, so this potassium nitrate is also an aqueous solution. Lead to iodide is insoluble, so that was a precipitation reaction. Okay, we formed some solid lead to iodide, and leaving it long enough, it would sink down to the bottom of the test tube. Now, by making solutions of the reactants, we're actually looking at something else. We're actually looking at surface area and we're looking at the fact that ions just react more quickly. Okay, so firstly, in surface area. Well, if you increase the surface area, the reaction rate increases. By making aqueous solutions of the reactants, that's essentially the ultimate of an increase in surface area. So we saw the reaction goes really, really fast. But also what we're doing is we don't have any lead nitrate molecules, and we don't have any potassium iodide molecules. What we actually have by making the aqueous solutions is, let's just edit this equation now. What we actually have are potassium ions in the aqueous solution. We also have, some iodide ions. We've got 2 of those as well in aqueous solution. We had 2 nitrates in aqueous solution, and we had some lead-2 ions in aqueous solution. There we go. That's what we actually have by dissolving the lead-2 nitrate and the potassium iodide in solution. In an aqueous solution, the ionic compounds are split up. So we're in ion form now, right? We've got lead-2 ions, we've got nitrate ions, potassium ions, and iodide ions. Okay, so far so good. We've done half the work. Okay, so remember, if we want to make something in chemistry, right, if we want to do a chemical reaction, all we're doing is rearranging the things that we have. We can't create or destroy, you just rearrange the bits that you have. We said right at the start that essentially the cations, the lead-2 and the K+, they just sort of switch places, right? The lead leaves the nitrate and goes over to the iodide, and the potassium leaves the iodide and hooks up with the nitrate. So we're doing this double displacement or metathesis reaction. So we're just rearranging what we have. Now, because in aqueous solutions we've already split up the compounds, all we need to do now is hook up the ions as a different rearrangement. So essentially what this is getting at is that ions react faster than compounds. Okay, you've already done half the work. The compounds that you started with of the reactant molecules have already split up. You've already broken those bonds. All you need to do now is form the new bonds of the products, right? So that's why the reaction goes so quickly in aqueous solution, because we've already got ions. We didn't need to break bonds of the lead nitrate, and we didn't need to break the bonds of the potassium iodide first. Okay, we've just got our ions ready to go, so they can hook straight up to make the products. So essentially, this video is firstly collision theory, that the reactant molecules need to collide first in order to have the reaction. Secondly, increase the surface area, the reaction will go more quickly. And thirdly, the fact that ions tend to react much more quickly than compounds.
Don't forget to hit the like button. Yeah, and subscribe to It's Up Here. And here's another video.